Oh, I messed up. Well, I think it not good, but when I look back at my answers, I didn't get a single one of the ones where I was like, unsure about. Okay. Oh. No, I didn't think that's great. But yeah. I think I put almost. That's right, because we had like a data, you know. That was like telling me like you can't reduce it. Because we like the Hagerrot. Yeah, it's a Hagerrot. Yeah. I was like, either I'm overthinking this question. Because everything has questions. Yeah. Everything has better be false. No, it definitely, I'm like pretty sure. Because like, the Harmonic group is already with oxidizing. Yeah. Oxidizing. Do you oxidize on the next? But like, that's just not like a thing. Yeah. You just don't do that. Like a biological oxidization. Yeah. That's just not it. So when I was thinking this, I was like, I don't know. And then I clicked on there. I ended up getting it right. But I couldn't remember the difference between like the font, like what the fonts look like. But I studied it.
Like on pan.
Yeah, I couldn't remember. And then I was like, I drew it, and I was like, you know what? Just gonna go with it. And I went with it, and it was actually really stuff. I did way better than I thought I could. And when I felt better, I was like, okay. Very interesting. I must have not, because I knew that I was supposed to focus on the cards because it was sketching the structure. And so I read put a lot down one second, but I must not have like already done that because I didn't update so that there's like homework, so I thought I missed it. And so like I did do it. And it's not good. No, I know, but I would have liked to have done that as it's the homework, you know. Yeah. So it's just like frustrating because I felt like there's a couple questions on there that I wouldn't have thought would be on the test, but they were on the homework, so I should have known that they were going to be on the test. Just fine. Oh, yeah, right? Yeah. I just thought that was a little fix on my part. So, yeah, it was like the Swenson computation and then the max velocity here. I don't know. It kind of went okay. We'll see. Felt better than the last. I studied.
Yes, the last one was.
I studied math. Okay, but only I studied maybe 4 hours. And for this test, I think it is really good. I love you. There's just so much happening.
Say, what's the bio?
We're figuring it out.
It's just interesting. You do it next. Test. I've already taken bio.
There was a question.
The last question. Single page. Please write your own non-trivial question on provided stage.
He said NESU 461 cheers.
It's just how they write. Do examples.
Yeah. This is it.
Yes, that's it.
Yeah.
Yes.
Yeah.
And she will be judging me. And I'm like, this year. Or maybe opposite. Better this time? Is it better this time? Last time you were complaining.
Slightly better.
Okay. Thank you. That's a good.
It's just like that really blurred picture. What's that? And then say something instead.
Well, if we want to make really good picture from this, probably I need to focus camera not on the content, but on the person.
How come my photo is the blurriest?
Because you were not on the Monday session, the Friday session when we were presenting during the photo.
Oh,
I
would
like
say that my
that.
picture went down and out way for last time.
Oh, okay.
Sad. Just kidding. It's fine.
I was trying not to reproduce the from previous one, but using most of data.
Oh, it's okay. I don't care.
Welcome to the physical chemistry 364. So, these class targets predicting outcomes of measurements. We are learning basic laws of wave in nature of electron and applying it to simple things. Because problems are mathematically complicated, we are trying to do it with a little bit of scientific computing. And today is the last presentation, which is technical. Next one will be absolutely last one. It will be very creative. It will be individual research projects. So the presenters are shown here. You don't remember names. And the order is abbreviated title. So the goal of today's meeting is that you teach each other. An expert in one question teaches the rest of the class to work easy with other things, and then we will apply the skills for individual research projects. If you never seen, PowerPoint windows, they are you select and run by clicking on this little symbol. So with this, I would like to invite to the stage Morgen, who will bring us basic principles of modeling dynamics of wave in nature of waves.
Perfect. All right. Well, as Dimitri said, I'll be kind of going over the wave packet propagation and just kind of the broad generalization of what we're all doing, and under that falls a few different operators. So the wave packet propagation, definition of a wave packet is variety of amounts of waves, sinusoidal waves that all travel in kind of like a little bundle or a packet, as the term goes. And they come in two parts, real or imaginary. And so I know there's the one line of code that we got those real and imaginary ones to come out within the main portion of the cell, which is the magnitude that we have.
If remote, or just quick touch.
Okay, perfect. So this section right here in the code is our wave packet, and it looks a lot less nice in code than it does on paper, but that is that section there. And then another important line that affects the code greatly is the P0, which is our momentum. So this value actually determines the distance and direction that the wave packet travels. If you remember, in the lab we added a 1 to the beginning of that, and it made it travel a lot farther over the course that the code ran. And then we put a negative that actually traveled in the opposite direction. And so that P0 is what determines kind of where the wave packet travels as the code is run. So then within that, the Hamiltonian is part of the evolution operator. And so the Hamiltonian is comprised of kinetic energy and potential energy. And in order to present this evolution operator correctly, we need to express the Hamiltonian as a matrix. And since kinetic energy is the momentum squared over 2 mass, that means that we're going to have to express the momentum operator as a matrix as well. So this is the portion of the code that covers our momentum operator, which was h bar with k here. And as it states within the code here, it says that this does have to be specified as a matrix. So we have to find the way to mathematically convert our momentum operator into a matrix. So I was trying to just like type this in, but the formatting was not really working with me, so I took a little chunk from the scan of the lab a couple weeks ago. So this is the way that we actually converted our momentum operator into a matrix. And we've got these diagonals here, depending on which, if you go positive or negative with that momentum operator. So here's our evolution operator. And the evolution operator is comprised of U times, U is the action times past state, which gives you the future state. Within U is that Hamiltonian, which is why in order to get our evolution operator as a matrix, we have to convert the Hamiltonian as well. And here indicated by the arrow is this very important line of code that Dimitri told us about. It's E-tau, which is very important because that is actually the code for our evolution operator that makes all of this stuff work in this wave packet. So when you first start running the code, it starts off standstill, and as you enter, we all saw it kind of starts as this sharp peak, and then as the code runs, it starts to flatten out and eventually ends completely flattened out like that. And these are just a few other graphs of the code here showing the time evolution and a few different little specifications of the code that ran. And then this was the final, kind of showing the probability of the locations for our wave packet as time moves on. So kind of to sum it up, the analogy that I thought fit pretty well was the Matryoshka dolls, where inside of your wave packet you have your evolution operator, which has the Hamiltonian inside of that, and contains the momentum operator. So that's kind of why these are all important to be shown together, because one kind of goes into the other in order to get you the final product, which is the wave packet.
Okay, let's thank Morgen. Presentation is open for discussion. questions about matryoshkas? Anyone? I would like to start. I have like 6 questions. So what is definition of momentum operator? The talk is great, but we want to polish details. Because if something is verbalized wrong, that may create deception for the class. No, just tell by words. Do not look there.
Okay. I thought you were going to go back. You meant definition of momentum operator?
Yes. Like if someone, stranger, catches you in the store and tells that you're a scientist, tell me what is momentum operator. You should, oh, it is one of these materials. But can you tell anything more?
Well, momentum operator is sort of like the initial push that the wave packet has. It's kind of what determines which way it goes and how far or fast it goes.
But what is the difference between operator and the value? Like, which plane wave has larger momentum? Where fringes are denser or fringes are sparser? Okay, so momentum is a thing that measures how dense are fringes. Okay? Answer that ipsos. Okay. The next is a killer question, so I realize it, and do not panic. Just try your best. We do have 2 representations. Stephen could be answering it later, but let you try. We have coordinate representation and momentum representation. And then we have 2 operators, position and momentum. And then we have so many overlaps. So position, operator, momentum representation, momentum in momentum and position representation. So, so what's the difference between momentum operator in momentum representation and position representation?
Difference in momentum operator position
representation, which actually what you're showing here, and momentum operator in momentum representation. If anyone has a clear idea and wants to help, it's very welcome in the little sign. For everyone it is optional, for Stephen it is mandatory. You will get the same question. Not for Stephen, sorry. For John. Stephen can relax. Kristen? Yes. So if the operator is in its own representation, then it is diagonal.
Oh,
very good. Yep. Okay. More questions to the speaker? Let's thank Morgen once again. And John will tell his story first and enlighten us more about momentum representation in coordinate and in momentum.
Wonderful. Thank you all for being here. Anyone watching in the future, also thank you. So I will be talking about a couple of different things. I'm going to do a quick overview of making a movie, which we have all done. It is pretty much the exact same process, but it is something that I am doing, so I will show you nonetheless. So creating movies with our current realm of code. I'm not sure. Oh, I can. So when you create the movie, this is what you end up with. Pretty neat. It's very pixelated, but you know, it's fine. Still see what's going on. And so you may be wondering, how do we actually make this happen? So it's pretty simple. I don't want to watch that. What we do is pretty much the exact same thing we've always done. Before we have the loop in the code, we put this first line. And I named this video because, you know, simple. In the loop, we put this. After the loop, we put this. and then you run the code. A video will be saved, and then you can do what you like with it. I put it in my PowerPoint. You can put it on YouTube. I'm not going to show you how, because I assume by now we know. So that's that. Exact same thing, just with that larger group that we have. So part 2 is the fun part. Commutation and conversion of operators. I'm going to try to go over them part by part, and hopefully it's effective. So, commutation. This is just a general overview. To start out, for commutation, the definition that we have A and B written in this notation, it is equal to AB minus BA. And then if AB minus BA is equal to 0, we can say A and B commute. So we can apply this to position and momentum in this form, which equals this, and then doing some basic math, you get to it being I times H bar, times the identity operator, which we have as 1 to the factor, I believe. But, yes. But we see here the equity or momentum and position and momentum do not as that equals 0, but that just means that you have to calculate them separately. They don't coincide when you're doing code. And so this actually has a definition XP for the I bar. It's the canonical commutation operator. So that's just a little bit about that. And then for some basics about conversion, we have this wonderful integral up here. This integral from infinity to infinity of, I want to say pi. I always forget what it's called, but times e raised to the negative I e over h bar. And so integrals aren't always easy. So we can consider it as a double integral with this times some matrix times this. And then eventually we can get rid of this entirely by writing it in the form of matrix. And so when we do that, we apply raw and head, and we go from momentum to position. And we have these double integrals right here, but we can get away from that by using these matrices. I hope I have it on the next slide. But kind of as Morgen was showing before, you have this type of matrix with the different values, kind of takes the integration and just replaces it with a string that moves it from the integral to the matrix, so you don't have to bother with that, which we have done with the Okay, so the application of this, if you look at the code. First, we have defined in the code that we're using the points to be 200, which is important because I'll wrap back to that one. What I think I got of this most. So basically, what I have here is just a list of everything that's defined, so we can actually see the important values and how we got them. So we have x defined here, from 1 to 200. All the values of the positions, and then we can find the position operator as the diagonal of that X matrix to form the matrix operator. So this is defined. That's important because we'll use it later. Then we have position operator, which a lot of this code is kind of what Morgen already showed, but I'm just going to go over it a little bit more. Operator equals to this, which is a vector, and then we get it to the matrix form again because we don't want to do it with vectors. Then we have all these values defined here, which there's a lot that have an impact there. We'll kind of skim over it just to do this W matrix that we formed using these different values. And this is used kind of like this format. We see that a similar format used here, using this, and then we have 2x defined using this momentum oscillator. And so finally, fun one, px3, we define as C1, and then we use this Toplitz, which I do not know what that meant, to define another value. So a little bit about Toplitz, what exactly that means, because it's fairly simple, but I didn't understand it, so I thought I might as well go over it. Basically, all the diagonal elements of this matrix are the same. So MATLAB uses this to just define a matrix with the diagonals all being the same, which in this case, they should all be 0, I believe. And basically, this is a 200 by 200 matrix, which is why the endpoint is important, because the x off, px, and px3 are all 200 by 200 matrices. So that is defined by the endpoints. If you switch that changes the size. So Toplitz as px3 is basically this matrix, just a special form that MATLAB uses.
We will launch synthetic algorithm. Just keep going.
Completely. Okay, so this is a lot of just kind of an overview of the code. I wanted to show some actual applications, what it might look like in MATLAB code, with messing around with some of that. So this is the graph of the position operated here. You can see mesh x off, what I typed there. And this is the imaginary values of the momentum operator. And then the final one, which is hard to look at, is the real value of the momentum operator. But you see it's kind of flat here, it starts to wave at the end, and then we have this forming in the middle, and then again for the wave at the far right side. And so we can multiply these in a variety of ways to get different looks. But first, this is px3. The imaginary value on the left hand, real on the right is the plane. This looks similar to px, but this is slightly different. And so we can multiply these together. I have every single one, I think. And I'm not going to go over them all in detail, but we have imaginary on the left, real on the right. So this is the x operator times px3 minus px3 times the x operator. Two forms of that. If you use px and px3 instead of px twice, you get this kind of shape waving down towards the middle for the real. This one I found interesting because once you flip the px and the px, you get it going the other way. And then if you use both the px, this form kind of collides and goes down like that. It looks cool. I'm not sure if you can really just understand what exactly it's showing by looking at it, but that's just kind of different ways you can use these different operators and values to form different figures. That is all I have.
Oh, not too many. Let's think. Questions. Were you able to confirm the commutation relation of position and momentum? Which of your results look at most close to expected Planck constant times unity metrics?
For computation.
Because the goal of this exercise was to check whether position and momentum operators commute.
From my initial findings, it didn't appear like they did.
But some of them show very, yeah, they shouldn't commute. Yeah. But what is the commutator of position and momentum? What is the commutator of position and momentum according to your computations in comparison to theoretical expectations?
So the theoretical should be I times h5.
Mm-hmm.
So you mean, what does it look like when you compute it with these graphs?
Mm-hmm.
I'll look at.
Would this yellow thing be the closest? Because Okay. More questions to John? If no, thank you once again. We are a little over time, but I think we can speed up a little. So, Alyssa will follow the general directions set up by Morgen with matryoshkas, and John explained as matryoshka with momentum, and Alyssa will tell about connection to wave function and overall dynamics.
Most of the information that I have on my slides has already been covered, so you just get to hear it again. Okay, so the only thing that is new information possibly on my PowerPoint slide that you haven't already heard is how you set up the initial conditions for the wave function. So this is just taken from one of our either this year, I can't remember exactly which one it was. But so you use the part that's in the little box there. That's the Gaussian distribution, which I'm going to go back and put in the next slide. So it makes it really nice, obviously, the Gaussian distribution shape for your wave function, but your initial conditions. And then you can put whatever wave packet you like in there. In this one, it's like the velocity of the wave packet. And then the square root of the dx, which is actually, I thought that it was going to be like a varying thing, but it's actually a number. I did not know that until I started to do this.
What happens if you change this number?
Then it can, like, the steps. Isn't it the stuff that it can
So it contracts or expands the range of definition?
Yeah. And so then also we've seen these a few times before, but we have different values that are defined in here so that we can find the psi naught, our initial wave function. So like we talked about the 200 points, and then in this case the initial momentum is 0, which is the p naught right here, and then the x naught is 40, which we can see on here where the x naught, like where it starts, is right in the middle. The distribution is right over 40, and then it's not moving currently, so that makes sense on the initial velocity is 0 at time 0 and it's not moving. And then when it's broken down into its imaginary and real parts, which is what this code does, and then the dots here, we get the nice dotted line. You can see that obviously the real and imaginary parts don't look like Gaussian functions by themselves, but when the absolute value is taken both of them, it brings back the original function that we had up there, which is in the yellow, which I realize is a terrible color, but yeah, it's there. Okay, so there are, what is in our code currently is there's 3 different methods to do like the mechanics, I guess, behind finding the values that we're looking at. I'm sure there's more out there, but I don't know them, so I only know the 3 that are in our code. So the first method is the momentum in momentum space, propagated in momentum space. So the wave packet is propagated in momentum space. And then it can be transferred to coordinate space, where the wave function is propagated in coordinate space, and which is both the same, so like momentum in momentum space and coordinate space. And then the bottom is a little bit different, where it's defined as the derivative of finite differences, which is where the Topolt's matrix comes to play. So I'll put that a little bit. Fair warning, my knowledge on it is a little minimal, because that matrix is difficult. So anyways, so in our code for the method 1, it has these values that we've seen before on previous presentations. And so it has all the values in momentum, and then it's the position operator that we talked about. So this is just the normal what we talked about previously. And then we also did talk about this too. So an alternate definition of momentum is to put it into the propagating coordinate space, which is p of x, and we use this function with all the same variables that we also talked about. So also taken care of. And then, oh, it had some ghost editing here. So the Topolt's matrix looks like this, where all of the diagonals are the same value. It doesn't have to be in order of like increasing or decreasing. It can be completely random order as long as all the diagonal values are the And so this is like the basically what this is the matrix of these different operators, which goes from I all the way to J. I'm pretty sure. Which can be like that length and that width. And so you just the A naught is on the diagonal, and then that can be varied depending on your initial conditions that you set. But I'm fairly certain that you put the momentum operator in this form, so then produce different values based on the multiplication of the momentum operator with the wave function. But yep. Anyways, that's it. Oh, not it. There's more. Oh, yeah. Okay, so this is the loop that is in the code that works for all three of the different methods, where you start with your very initial pass wave function, which is just the psi, and then as each loop goes, you add another form of the exponential, the evolution operator, which you can just add in the exponential. So that's how it works. And yeah, pretty much it.
Okay, let's thank Alyssa. Please do not leave. There could be tons of questions. Presentation is open for discussion, and I will give a question not about equations, more about general directions. Why any of us need these presentations and equations in the following sense? Is there any benefit to independent research projects? Is there any benefit of this presentation up to the end of the course?
Hopefully.
How do you project?
Probably there's different, I'm sure that each method has a time constraint attached to it. So there might be one that's more accurate than the other, but it just takes more time to compute. So you might need to weigh your options as far as how long. I mean, that's a practical sense of it, probably.
Excellent. Very scientific, non-selfish answer. There is I do have a more cynic answer. There will be guests, like students, graduate students, faculty to the final presentations, and they're not here because it's repeating from year to year. And when you present your individual projects, instead of asking project, there will be questions. How does the code work? So it's, in some sense, you are practicing how to answer this question. Okay. More questions to Alyssa? If no, let's thank her once again. So, Steven. So Alyssa thought that there are some time constraints when for some duration one can apply the code, for some one cannot. And maybe Steven can teach us about it.
Well, talking about modeling discrete wave functions, simulation, so a little bit nervous. It's kind of short of all the theory of that function. So first of all, what is a discrete wave function? The simplest answer is it's a wave function with discrete integer values that allow us to model the equation over a set interval of space and time. Since a wave function, obviously, the probability of finding an electron in a certain area, and probability is defined mathematically as the area under a function. A discrete wave function therefore allows us to calculate the probability of the wave function's location. As we've seen in the previous presentations, wave function starts out very high, and then over time it gets flatter, which I'm talking about. So what that represents is really the probability of finding the electron in a specific location is lower and lower. So it will take larger and larger intervals to have the same probability to find it. I think that's correct. Size versus time. I was just getting into that. So from the code, we can see the original P naught with a momentum of 0.425 gives us this sort of top-down view of the function where it starts out at time 0 with very, very high and a very, very high probability of finding the electron in that area. And then as time progresses, it gets wider and wider. It's almost as flat as 0. And we have to take over an entire infinitely large area to have to find it. So, about that. And so what Dr. Killen demonstrated in the lab last week, I believe, is if you increase the P0, you run into a problem with the code as it's written. And that is the electron wraps around back into the simulation, which is not really possible, even in the most quantum entanglement sense of electrons. But what's happening there really is that I believe this would have to do with the repeating values of the matrix, where it forms a diagonal line that's moving through space to represent the change of the wave function. We reach the edge of our simulated space where we're calculating it, and so we end up wrapping back around to the other edge of reality that we continue off in one direction, changing with time. This is also what we see a little bit with how the end of the curve starts to pop back up a little bit with the movie that a few of you have shown before. That is also a limitation that we can see. This is just sort of the top-down view of all of those different frames stacked next to each other. So what is normalization? Dr. Killen was helpful enough to annotate this for me, but a couple of things that I was missing. Oh, you did update it. Thank you. So this is the one that I wrote. So we have our wave packet here with our momentum and our operators. And as you can see, we have two functions labeled normal. We have the last part, the fourth loop. We also have this square root of dx. So our wave packet would be written in an integral form as the integral of negative infinity to positive infinity of dx of psi star and psi with a probability of 1. And by splitting that into the square root of dx, which allows us to break it into two parts, we can take that as a summation of the time rather than an integral. It allows us to algebraically find the value of the wave. So, like I said, it allows us to algebraically find the area under the function without having to take a massive integral from negative infinity to positive infinity, and just simplifies the way that the calculation is.
Okay, thanks, Steven. Please hear any questions, comments, or anyone see observes some errors that we want to fix right away to avoid deception in the community. So anything, and Steven, you're also invited to find anything that can be improved.
The diagonality of the function versus time, that is related to the diagonal values of the matrix. No?
Everything is perfect and correct except this way. There are like 4 places that one may want to correct. Where?
The exponential, like the non-zero velocity wavepacket, but below it says
Oh, P0?
not P0, it's IL. Or,
Oh, okay. So it's a typo. It's, instead of II, it is I. You mean here? Yeah, but it's a typo. We can close our eyes. Computer will tell, will report error. Anything. Anything that violates sense of Gaussian function. How do we define the width of a Gaussian function if you want to control the width? Yes. And where does variance pop up? Where does it appear? Let's look on the equation in the purple box. And you're welcome to react quicker than anyone else. So, where should X bar come? Should it be?
That should be under there.
In the
This should be under that.
Right? So let's correct it right now because no, maybe I'll do this. Right? Anything else? So the lower line shows integral in standard form and then in the summation as we do. And probably if there is an index of summation, sum sub I, the same index should be.
This should be a sub I.
No, summation sub I. It means summation over index I. And then your wave function should have, instead of x, we are defined in the. More questions or suggestions? Everyone agrees with the changes. But it was really right and useful explanation of the limitations. So one needs to use longer or shorter interval of time to avoid this problem, right?
A shorter interval of time, if you want to model a very higher initial velocity, you need a shorter interval of time or a much larger space.
Okay.
So I believe a shorter interval of time is easier to model in code. That's probably what.
Yep, sounds great. Let's thank Steven once again. So with Kristen, we have 3 presentations for remaining 10 minutes.
well, 3 minutes each.
We got it. 3-minute presentations.
Yeah, sorry, I wasn't energetic enough to cut first speakers.
So I can talk a little bit about the expectation values of our observables and then uncertainty of position and momentum. If I can hear it. So first, we looked at the accumulation of expectation values. In this case, we're talking about position. Just to clarify, our expectation values are essentially our predicted values of position for the wave packet in the future. So that's kind of the output of our wave function calculations that we do. To find our position, we're going to do the summation of probability times our position value, so that's x. And then here we have in the bracket notation x is equal to the integral of our wave function times our position. So in the code, what we do is we leave this summation up here an actual name. In this case, it's AVG3. It's not average, so I was confused with that for a second, but it's actually not taking the average of that, which is in that summation stuff. And that's this first plot up here on the top. And then if we wanted to plot that expectation value across a sum of values, we can do the second plot, which is showing the progression of that wave packet position. Then if we do the same thing but for momentum, the math is actually a little bit different in this case. We're going to do a row by column multiplication of matrices. In this case, we also have EVEC, which is our matrix operator for momentum that we've already heard a lot about today. So we don't have to cover that. Psi star is our wave function at a given time, and psi is a given wave function. I have up here in the code what that looks like. We have our psi 3, that apostrophe is indicating psi star, times our momentum operator, and then it's divided by a normalization factor. So like Stephen talked about, that way we're going to normalize the function. Since in free space, momentum is constant with respect to time, Oh, did I delete the graph? It would just be a straight line. I took it out accidentally. And so if you plot it, then for the real values is when you see an actual chart instead of just a straight line at 0, which is essentially what we saw 2 in Morgen. So we had that diagonal at 0, momentum in free space, then momentum space. Then you have uncertainty of position, which is essentially the width of the Gaussian function, and so, or the width of the wave packet. So to apply variance to our previously plotted data, we can get a numerical value for the uncertainty of position. So I have up here sigma, which is the uncertainty value, and the integral given to define sigma, which is, like we talked about in lab, variance for the square of standard deviation. And so that's a value that's going to grow quadratically over time. And if you were to do that for momentum, it's the exact same method, but you replace your position values for momentum values. In this case, I didn't have a chance to put in the video, but if you were to watch this plot, it's going to oscillate back and forth, and you're getting oscillations up and down for when your wave packet is hitting the wall of the box.
But if it doesn't hit the wall of the box, it stays constant, which is predicted. Like first, from 0 to 100, it stays flat, right?
Yeah.
So you were not obeying the recommendation of Stephen and to run the long time.
This takes a lot longer. Then we also touched briefly on expectation values for energy. I wasn't able to add a lot of information on this, but in our code we had defined E0 or E naught as our quantum width. And then in order to run this operation, we had our row times an operator ham and then times our column. This is similar to the operation that we did for the accumulation of momentum values. And then we have another, when you do this, the output is an E3, which is our quantum approach for energy. And then the difference of those two values is going to give us a quantitative measure. There was a word there. Quantum
Feature.
There was a word that don't have it. And then lastly, we wanted to just kind of overview of how to save your numerical data. We've done this before, so it's nothing too crazy. You enter your save function or command in MATLAB, so it's ASCII, and then a file name. And if you wanted to export this to Excel, there's a couple different ways you can do it. The easiest one being just to open it into Notebook, copy and paste, but otherwise, export it.
Okay, let's thank Kristen for the presentation. Are there any questions? If no, let's thank Kristen once again. Next presentation is by Amelia. We have 2 talks for 4 minutes.
Okay, so mine is on visualization in MATLAB. Here you have the real part and the dotted line, and the imaginary part, and then when you take the absolute value of both of them, you get the Gaussian line over the top. And then for this wave packet, the Gaussian line would be over the top as well. And then this other plot is the potential energy that it would need to reach in order for the chemical reaction to move forward or proceed. And in this one, it wouldn't reach it, so it wouldn't keep going. And to plot any observable, you just plot type of plot, and then all of your dependent and independent variables. And then obviously, the more variables you have, the more complicated your graph would be. And then you can organize data in MATLAB or bundle groups of observables, and you can use the grouping function by defining a group, like just G, and then you basically just type it in brackets, and then you can take those variables out of your plot in order to make it more simplified and just have the important information that you want to look at and analyze. And then these are just the specific lines of code that refer to each of these plots. And you know, your probability plot on the top, and then your position, and then
Dispersion, variance, mixed.
and more code. And then this is just the plot that
Steven was showing.
Steven showed us already. And just your probability of position.
Okay, let's thank Amelia. Are there any questions? If there are no more questions, let's thank Amelia once again. And the last but not least presentation by Eungyo. In 2 minutes. Let's check if.
Please feel free to leave. If you have other classes or other appointments.
So check if the movies work.
Yeah.
If they don't, we'll use your laptop. Works? Yes.
Yeah, I think it
Okay.
Alright, hi, my name is Yohang, and today I'm going to talk about the application of Wavepackets codes to Box's barrier and Harmonic oscillator. First of all, I'm just going to talk about a little bit about the use parameters. P0 is the initial momentum, and X node is the initial position, and X VAR is the width of the initial wave packet. U2 is the height of the movement, and variable AB is the half width of the barrier or box. So first, it is 1D finite box. It has a set depth, which is I set -10, which worked well. So this is a animation of how 1D finite box works. So once the wave goes into the box, it causes an oscillation.
So part of wave transmits through, but parts reflects, and parts is getting trapped.
Yes. Part of it is just trapped, and some part has escaped. X node, as I talked to you previously, it's the initial position of X. So this has a higher X node, which is 20, and this has a lower X, which is like about 10. I'll show you this. So this is higher X node. And this is lower X node. Since the energy is consumed on its way of traveling, so higher X node, so the amount of energy escaped from the box is higher in higher X node. And this is 1D infinite box. It has an infinite depth, which is like, in my case, -6 was enough for making an infinite box. So still, I tested the depth of 30, and some portion of the wave still able to escape. And when I tested -60, none of the wave has escaped. So well. So I tested lower X node.
And now it is barrier instead of wall, right?
That's right. This is a barrier, which is a positive U2 value. And this is higher X node, which is just started right next to the barrier. And more portion of wave has escaped. Every other values are the same, except for X node. And I tested a higher X node, our barrier. Of course, less amount of wave was successful to escape. Yeah, so it worked on box as well. So I tested infinite big barrier, and of course, none of the wave were successful to escape the infinite barrier. So the other variable used is AB value, which is the width of the barrier, and it has a lower AB and higher AB value, which is 15. Makes such things. And this is Harmonic oscillator. Instead of the barrier, it has a tube under which has a parabolic shape, and the wave has to oscillate within the harmonic oscillator, within the parabolic shape. So the importance of the application of the wave packet in 1D box barrier and the harmonic oscillator is highly related to the movement of electrons. So it's really important to determine the ionization energy with MATLAB. Thank you.
Okay, well, thank you. Any questions? If there are no questions, let's keep it here. But thank you once again. Brief comment about his presentation. It's not a question. I want to show something that you're pretty good.
Yeah.
Eungyo was changing initial position of wavepacket. It would be more productive in the future projects to change momentum. So position is just how close it is, and changing momentum is it above or below the barrier. And basically, what you did is an image of our independent research projects. We will just try different potentials and run it with different initial conditions. So with this, I would like to announce our meeting complete. Everyone gets credits equivalent to successful homeworks, and looking forward to see you on Wednesday.